Hi everyone! So in this video, we're going to be talking about special types of functions that are called even and odd functions. And so we'll see that not every function is even or odd. It's basically just a sort of special category of function that certain functions belong to. So in order to get the ball rolling on this topic, I'd like you to do kind of a warm-up. So I'd like you to pause the video and sketch the graphs of f of x is equal to x squared, g of x is equal to x cubed, and h of x is equal to square root of x, and then graph f of negative x, g of negative x, and h of negative x. And we'll see that that will allow us to talk about what even and odd functions look like. Okay, so let's start with the first function. So the first function we're going to graph f of x in purple. So I'm just going to graph the original function f of x is equal to x squared. And then we'll graph f of negative x. Okay, so what would f of negative x look like? Well, it would be reflected about the y-axis, right? Because we're negating the input, and so it's a horizontal reflection, which means we're reflecting over the y-axis. So it's reflected about the y-axis. So let's try to sketch what that would look like. So if we took this graph, f of x, and we reflected it over the y-axis, well, we would get the exact same graph, right? I'll draw it here, but it would look exactly the same as the original graph. And so that's because this graph has a special type of symmetry. And it turns out that graphs that have this type of symmetry are what are called even functions. So in this case, f of x is the same as f of negative x, right? Basically, what I'm saying here is that the original graph is the same as the graph that you get by reflecting about the y-axis. And so this tells us that f of x, our original function, f of x is equal to x squared, is what's called an even function. So you might be thinking, it's called an even function because x squared, 2 is an even number. There is a relationship between the exponents and whether the function's even or odd, but we'll see that there are plenty of examples of even and odd functions that don't have even or odd numbers involved at all. So I really want you throughout this video, when you hear the word even, try to separate that word out from what you think it means. And when you hear odd, try to separate it out from what you think it means. So truly, even and odd in this video, think of it as like you've never heard that word before in your life and you're learning a new definition for it. So the reason that this graph is called an even function, or this function is called an even function, it's not because of the even number, it's because it has this special property where it is symmetric about the y-axis. When we reflect it over the y-axis, we get the same thing. So let's look at the next example, and then once we have seen these three examples, we'll write down some definitions. Okay, so the next one we were going to do is g of x is equal to x cubed. So let's start by graphing that. So cubic graph, I'm just going to plot a few points on this. Okay, so it looks something like this. Okay, so let's start by sketching g of negative x. So g of negative x is supposed to be a reflection, again, about the y-axis. Or I should say is reflected So we just want to take this graph and reflect it about the y-axis. So what will that give us? Well, that will give us a graph that looks like this. So you can do this again, as you hopefully remember from earlier videos. You can do this reflection by just switching the sign of every, in this case, every x coordinate, right? Because when you switch the sign of the x coordinate, that gives you a reflection over the y-axis, which is a horizontal reflection. Okay, so this graph does not look the same as the beginning one, right? It would not be true to say that g of x is equal to g of negative x. This one it was true, right? F of x was the same graph as f of negative x. This one they're different. However, I want to actually graph something else to kind of throw into the mix to compare. So let's graph actually negative g of x. So that would be taking your original graph and reflecting it now about the x-axis. So forget about the orange graph for a second, and let's just focus again on the original graph. And we're going to take that original graph and we're just going to reflect it over the x-axis. And so what does that mean? Well, it means that all of the y coordinates are going to flip signs. And so if you think about it, your graph is going to look like this. So it's actually going to look exactly the same as the graph of g of negative x. And so basically, in the previous example, we saw that reflecting over the y-axis gave you your original function. That's not the case here. But what we can say is that reflecting over the y-axis is the same as reflecting over the x-axis. Those two graphs are the same. The orange and the green graph are the same. And so this is because this function, so we said that having the property the one above had was called an even function. In this case, g of x is called an odd function. Again, it is related to the fact that we have this x cubed, but I don't want you to think that that's like the entire reason that we're using the word odd. And let me actually add in just what the function was, just so you have it there in your notes. So the reason that we're calling it an odd function is because it has this special property. The property that when you reflect it about the y-axis and when you reflect it about the x-axis, it looks exactly the same. That's what it means to be an odd function. It's not because the exponent is odd, it's because of the shape of the graph, because it has this special reflection property. Okay, so let's do our last example, which was h of x is equal to square root of x. So that graph looks like this. And so we are supposed to, in this case, just graph h of negative x. And so again, that is going to be a reflection about the y-axis. And so what do we get? We get a graph like this. So we can see already that the original function h of x is not the same as the reflected version, right? So that tells us that h of x is not an even function. So in order for a function to be an even function, it has to have this reflection property that we saw in the first one. This one does not have that property. So let's also compare, just to kind of be consistent with the last example, let's see what we get when we reflect over the x-axis instead. So if we do negative h of x, well, then that would give us a graph that looks like this. So again, remember, we're reflecting the original function still. So if we reflect the original function about the x-axis instead of the y-axis, we would get this green graph. So we can also see that h of negative x is not the same as negative h of x, right? So in the second example we did, it was true that when you reflected it one way, you got the same result as reflecting it the other way. This one does not have that property. And so basically this tells us that h of x is equal to square root of x, our original function, is neither even nor odd. So as I mentioned at the beginning, not all functions are either even or odd. There are some functions that are neither. So if it doesn't have either of those two reflection properties, it's neither. Okay, so I want to kind of formally define what it means for a function to be even or odd and kind of a few different ways that you can think about it. And then we'll look at some more examples so that you can see that it's not all about the exponents. So f of x, any function f of x, is called an even function if f of negative x is equal to f of x. So if reflecting about the y-axis gives you the same result as your original function. So I'm going to write that down. Actually, I want to kind of write down a few different ways that you can think about this definition. So the first one is that reflecting about the y-axis, right, because that's what f of negative x looks like, basically reflecting about the y-axis gives you the same graph as the original graph. Hopefully this color coding makes sense, right? I'm saying that basically what does this equation mean? It means that if you take that function and reflect it about the y-axis, you get exactly the same function you started with. And so this type of symmetry is called symmetry about the y-axis. So if you ever hear that, a graph is symmetric about the y-axis, that just means that when you reflect it over the y-axis, it looks exactly the same as it originally did. So there's another way that we can think about this definition of an even function, which is that, so what's another way of interpreting what f of negative x means? Well, you could imagine that x represents a number, some number, maybe x is 1 or 2 or 3. And so f of negative x would mean that instead of plugging in your original number, you're plugging in the negative of that number. So plugging in the negative of a number gives you the same result as plugging in the original number. So again, this color coding is supposed to kind of suggest different ways to understand this statement, right? So we can think of this statement as being a statement about transformations, but we can also think about this statement as a statement about plugging in numbers, right? So f of -2 is the same as f of +2, or f of 1 is the same as f of -1. So it's just saying that any number x that you pick, you get the same result whether you plug in a positive or negative. So let me just go back real quick to understand, why does that work here? Well, here is our example of an even function. And so for example, the original even function has the points 2, 4, and -2, 4, right? So plugging in the negative or positive version of the same number, it gives you the same result. F of 2 is the same as f of -2. And hopefully you can understand why that's actually equivalent to the symmetry idea, right? Because if you have 2 points that are kind of equidistant from the y-axis and they're at the same height, and if you have those kinds of points all along, well, that's going to give you a graph that is symmetric about the y-axis. Okay, so I want to give you a few more examples of even functions. So the first example that we already saw was f of x is equal to x squared. I'm just going to sketch a quick little mini picture of it just so we can kind of confirm that it has that symmetry that we were talking about. And then in addition to it having the symmetry, like we just saw, it also has that property where when you plug in a positive and negative version of the same number, you get the same result. So what's another example? Like maybe think back to, these sort of like basic functions that we've been using for transformations. What is another example of those functions that has this same kind of symmetry shape. So another one that we've been seeing is f of x is equal to absolute value of x, right? That function also has this shape where it is symmetric about the y-axis. And so I'm showing you this example because notice there is like no even or odd number involved in this function at all, but it still is considered an even function. So even function does not mean even exponent. It doesn't mean even number. It just means that it has this special kind of symmetry. It's symmetric about the y-axis. You could also have a function that, maybe doesn't even have a formula defined for it. So I'm just going to sketch a random function that would be considered an even function. So this function I'm about to sketch would be an even function if I can do a good enough job of drawing it. So this would be also an even function. Like literally any function that is symmetric about the y-axis is called even. So I want to show you a couple more examples. I'm going to pull up Desmos. So there's one function that we're not going to talk about in this class, but that you'll learn about in the next class, which is cosine. So you might have, if you've taken trigonometry before, you might have seen this graph. So I'm just going to make a note here so that if you see this in your notes later, you're not like, what is that? So you'll learn about this. Or I should say you'll learn because you'll talk all about this in Math 142. So we're not going to be talking about this function at all, but I just wanted to mention it because it's another good example of an even function when there's no even numbers to be found anywhere. So what does the graph of cosine look like? It looks like this. So notice that it has this like wave pattern, but it's symmetric about the y-axis, right? We see that whatever it's doing on the right, it's doing the exact same shape on the left. One more example is f of x is equal to x to the 2/3. So again, this one actually has an even and an odd number involved in it, but we can see that it has that kind of symmetry about the y-axis. Okay, so we're going to continue to define now what odd functions look like, and then we'll do a few problems where we have to actually figure out whether a function is even or odd or neither. Okay, so next up we have f of x is called an odd function if, so similarly before, so our definition up here, right, was f of negative x is equal to f of x. In this case, it's going to be f of negative x is equal to negative f of x. So how do we interpret that, when we were looking at that graph at the beginning? Well, we basically just were saying that reflecting over the, let me just make sure I'm consistent with how I word this here. So reflecting about the y-axis basically gives you the same graph. So I just want to make sure I'm, again, writing it kind of the same. I'll say it like this, is equivalent to reflecting about the y or the x-axis. Right? That's how we can interpret this equation above. F of negative x would mean reflecting about the y-axis, and then we're saying it's equal to, it's the same as reflecting about the x-axis. And so just like, how in the previous example, we talked about how that was called symmetry or symmetric about the y-axis. For this kind of function, it has a different name. It's called symmetric about the origin. So graphs that have this property of basically that, the fact that reflecting in one way is the same as reflecting in the other way, they're called symmetric about the origin. And I think symmetry about the origin is a little bit harder to kind of visualize than symmetry about the y-axis, but we'll look at a few more examples that I hope will kind of help you be able to see why these functions kind of look the way they do, or what odd functions have in common in terms of their shape. So one other thing, when we were talking about even functions, we also interpreted the thing in the box not as a statement about reflections, but instead as a statement about plugging in numbers. So I want to do the same thing here. So what is this saying? Well, f of negative x again would mean plugging in the negative of a number x gives the same result. That's what you can think of the equal sign as meaning. The same, oh my gosh, my brain stopped working. The same result as, and then what can we think of the right-hand side as meaning? Well, it's not the same as the original number, it's the negative, right? The negative of the result. I know the sentence I'm writing down right now is probably a little confusing. Don't worry, I'll go back and kind of parse what I mean by it. Okay, so what do I mean by this? I said plugging in the negative of a number x gives the same result as the negative of plugging in the original number x. So basically what I mean by that is, let's say you were to plug in 2 and negative 2. You wouldn't get the same result, you would get opposite results. So let's go back to our example of an odd function and see how that kind of plays out. So again, we need to be focusing on our original function here, right? We're talking about g of x is equal to x cubed. So for example, when you plug 2 into the function, you get 8, right? So f of 2, or I guess g of 2 is equal to 8. If you plug in negative 2, you get negative 8. So g of negative 2 is equal to negative 8. So the idea is that you're not getting the same result when you plug in a positive and negative of the same number. You're getting opposite results. So it's not like you're getting g of 2 is equal to 8 and then g of negative 2 is equal to like 7. You're getting negative 8. Like you're specifically getting the opposite result as you would when you plugged in the original number. And so that gives the graph this kind of like diagonal symmetry, right? That's how you can sort of think about symmetry about the origin, is that it's doing the same shape, but it's doing the same shape diagonally across from each other. Whereas with a function that's symmetric about the y-axis, it's doing the same shape on the right and on the left. This one is doing the same shape, but kind of flipped diagonally. So that's what graphs that are odd are always going to look like. They're going to have this kind of diagonal symmetry. Okay, so let's brainstorm again a few examples of odd functions. So one example would be f of x is equal to x cubed. We already saw that. I'm going to sketch a quick little picture of it. So it does have this kind of diagonal symmetry shape. Another example would be a linear function. So, and specifically a linear function that goes through the origin. So let's say f of x is equal to 2x. So what would the shape of that look like? Well, it would be a line with a slope of 2 and a y-intercept of 0. So that would look like this. And so that also has that same kind of symmetry, right? Whatever's going on in like the first quadrant, as you go up and to the right, you're having the same thing happen as you go down and to the left. Another example would just be, I'm just going to sketch a function that I'm not even going to tell you a formula for it, but a function that looks like this. Just trying to decide what color to use. A function that looks like this would also be called an odd function. So see how it also has that kind of symmetry where it's doing the same kind of shape, but like diagonally across from each other. Another example would be, we talked about above that graph called cosine of x. That's a trig function you'll learn about in your next math class. Similarly, there's a function called sine of x, which again, you'll learn about this. I'll just write math 142. But I'll show you what that graph looks like. So here's the graph of sine of x. So you can see, so let me pull back up cosine of x so we can compare. So cosine of x, remember, had that symmetry about the y-axis. Now, if we compare that to sine of x has a very similar shape, but it's now has this kind of symmetry where it goes like up and to the right and then down to the left, and it's doing the same shape but diagonally across from each other. So that's what an odd function looks like. Okay, so the next thing I want to do, I guess actually I'll say one more thing on this page, is that a function is called neither even nor odd if neither f is equal, or neither f of negative x is equal to x, or sorry, f of x, nor f of negative x is equal to negative f of x. So there are plenty of functions out there that do not satisfy either of these rules, that don't have these special types of symmetry. Okay, so I want to do a few examples, and in these we're going to basically determine whether the functions are even or odd, and we're going to do it two different ways. We're first going to kind of test out some numbers to try to help us get an idea of whether it seems like it's even or odd, and then we're also going to look at the graph as a confirmation of seeing that symmetry. So determine whether the following functions are even, odd, or neither. Okay, so first one I want to do is f of x is equal to negative x squared plus 5. So like I said, we'll think about the graph shape in a moment, but first let's try to test some numbers. And so when I'm talking about testing numbers, basically what I mean is that we want to test whether when we plug in a negative and positive of the same number, so like for example, -1 and +1, or -2 and +2, do we get the same result? Do we get opposite results? Do we get two completely different results? That will determine whether it's even, odd, or neither. So let's try f of 1 and f of -1. Okay, so if we plug in f of 1, we're going to get -1 squared. So remember that negative is not inside the parentheses, so it gets applied after. So that's going to be -1 plus 5, which is 4. On the other hand, if we plug in -1, well, now we have this negative sign outside, but we also have a negative sign inside that's getting squared. And so that is still going to be -1, right? Because the negative sign inside, that goes away when we square it, but then we still have a negative sign on the outside. And so we still get 4. So this is the same result. In other words, we just saw that f of -x is the same as f of +x. And so this doesn't absolutely prove that this is an even function. In order to prove that it was an even function, we would need to test every single x value out there. But this is at least some evidence in support of the fact that it's an even function. So I'm going to write down it's an even function. Again, it's not a super important distinction, but logically we're not proving it's an even function. It is. If you wanted, you could try some more numbers to really kind of get more of a sense of why it is. But why is it that we got the same result either way? It's basically because when you square a number, it doesn't matter whether that number is positive or negative. So regardless of whether we plug in 1 and -1, 2 and -2, 3 and -3, any two numbers we plug in, because we're squaring them, we're going to get the same result. So let's look at what the graph looks like to kind of confirm whether this is an even function. And this is one that you could graph by hand, right? We know how to graph this with transformation. So this should be, it was -x squared, so that should be reflected vertically and then shifted up by 5. And so that looks like that. And so we can see that this does have symmetry about the y-axis. Okay, next example. So this function is g of x is equal to 3x cubed minus x. So this one we don't know how to graph by hand. I'll pull the graph up a little later, but let's start by testing out some numbers. So again, we could do 1 and -1, we could do 2 and -2. Let's just pick some, let's just do 1 and -1 because that's kind of the easiest numbers to plug in. Okay, so what do we get when we plug in 1? Well, we get 3 times 1 cubed minus 1. And so that's going to be 3 minus 1, and that's 2. Now, what do we get when we plug in -1? Well, we get 3 times -1 cubed minus -1. So what is that going to equal? Well, -1 cubed is still negative, right? -1 times -1 times -1 is -1. So we end up with -3. And then here we have minus -1, that becomes +1. And so that is -2. And so notice that we didn't get the same result, we got opposite results. So f of -x was the opposite of f of x. And so this suggests that it's an odd function. Again, it doesn't prove it. We would need to somehow test every single number out there to really prove it, which isn't really a thing, but we can see why it worked, right? So why was it that we got the opposite result? Well, basically because both on this part and on this part, we were plugging, we ended up with kind of the opposite result we did in the first one, right? In the first one, we ended up with 3 minus 1. In the second one, we ended up with -3 plus 1. So both signs flipped, and that gave us the opposite result at the end of the day. So let's check out what that graph looks like. So this graph looks like this, and we can see that does have the shape that we saw for odd functions, right? It does kind of the same shape on the left and the right, but it kind of does it in the opposite direction. Okay, last example I want to do is h of x is equal to x minus 3 squared. So you might look at this and say, oh, look, it has a square, it's even, right? It has an even exponent. But we'll see that this actually does not end up being an even function. So this is why it's so important that you actually understand the definition of even and odd functions, and you're not just kind of looking at exponents. So let's test out, again, let's do 1 and -1. Okay, so if we plug in 1, we get 1 minus 3 squared. And so 1 minus 3 is equal to -2. So we have -2 squared. -2 squared is equal to 4. Okay, what if we plug in -1? Then we have -1 minus 3 squared. And so what's -1 minus 3? Well, that's -4. And what is -4 squared? That's 16. And so we plugged in opposite results or opposite numbers, and we got completely different results, right? They're not the same, they're not opposites, they're just completely different results. So completely different. And so this really tells us this could not be even or odd. So we can tell that f of -x is not the same as f of x, right? We didn't get the same result. And then we also saw that f of -x is not the same as -f of x. We didn't get opposite results either. And so that tells us that it's neither even nor odd. So what would this graph look like? Well, I'll pull it up in a second, but this is a parabola shifted to the right by 3, right? It's a horizontal shift. And so what we'll see is that even though it has this kind of symmetric looking shape, it's not actually symmetric about the y-axis, right? In order for it to be, sorry, I was just trying to change the color. In order for it to be an even function, it would need to be symmetric about the y-axis, and it's not. It is symmetric. It's symmetric about the line x is equal to 3. But it's not symmetric about the y-axis. We don't see the same shape happening on both sides of the y-axis. And so this is a function that is neither even nor odd. So that's it for this video. Basically, even and odd functions, it's not the most important topic. It is going to come up again in 142 and then also in 152, so Calculus 2. And basically, the main thing I just want you to get out of this video is understanding what this definition means, like seeing this definition of, even means f of -x is equal to f of x, odd means f of -x is equal to -f of x. I just really wanted to give you a way to understand what those definitions mean. And then I also want you to be able to recognize whether a function is even, odd, or neither by looking at its graph or plugging in numbers.